talking about polar and rectangular coordinates leads straight into the talk of vectors. Now what a vector is just a quantity with magnitude and a direction. The magnitude corresponds to the length of this thing we call a vector, and the direction talks about the angle relative to standard position. So this blue arrow, if you will, represents our vector. It has a length, which can be described as the magnitude, and it has a direction or an angle from standard position that we can calculate. Some verbiage. If I have a vector, it emanates from the origin, and we call that piece the tail. It ends somewhere out in space, and we call that the tip. The angle it makes with the standard position is theta. I can name vectors pretty much two ways, and they're both named by this odd form of a coordinate. You can tell it's a vector by the shape of the brackets that the point lies within. So you'll see here that this vector is in polar form. In other words, we're given the radius or the length of the segment. This is the magnitude. And how far it is from the standard position. In other words, its direction. Notice the bracketing that takes place. It's not parentheses. Parentheses indicate points. These brackets indicate it's a vector. Notation for vectors is this half arrow, if you will, above a letter. Now, you'll notice this guy's in polar form because it has an angle. This is in what's called component or rectangular form. Rectangular forms talk about a vector having an x component and a y component, much like an xy point. Although this is a point, notice its bracketing, it's parentheses, and this is a vector, notice its bracketing, looks like a greater than less than type bracket. If we want to talk angles that have the same magnitude but going in the opposite direction, if I want to flip this angle over in the other direction, I can do it a couple of different ways. But the best way to do that is to take and indicate, well, I have the negative vector, which gives us a negative radius, or this -4 leading, and the 20 degrees. And remember that -4 leading can be written as 4 and then 20 plus the 180 degrees. We covered that in our polar coordinate discussion. Now if I want to take and move the vector -6, 2, then all I really have to do is once again put a negative in front of the vector b. But in this case, since each is a coordinate point, I just go the opposite direction of each one of those coordinates. So -6 becomes +6, +2 becomes -2. Vectors can be drawn anywhere in space, but are typically named by one coordinate relative to standard position. In other words, you take the tail of your vector, slide it to the origin, and make sure that your vector is still pointing in the same relative direction as it was out in space. In order to calculate that point, to name it as a unique coordinate, we're going to take the tip minus the tail of the x coordinates and the y coordinates in each. So, if we take a look at vector A, I want to use the tip minus tail method for the x's. In other words, -1 minus -4. And then the tip minus tail method for the y's of 1 minus 4. Notice this gets me a vector of 3 and -3. Think about where that would land if I were to start at the origin. 3, -3 would be somewhere in the fourth quadrant. And if I look at the initial vector, it's pointing in the same relative direction, it's just slid down. Let's do the same for the rest of these. Vector B would be 5 minus 2 and 7 minus 2. or 3 and 5. And looking at the vector 3 and 5, that would be pointing somewhere in the first quadrant, like so. And that's relatively the same look as I had with the vector out in space. Vector C is given by the tip minus tail method again, so I have negative 5 minus negative 3 and negative 2 minus negative 8. This yields negative 2 and 6, and if I look at where negative 2, 6 would be, it's pointing somewhere out into that second quadrant area, which is roughly what that vector is doing there. Finally, vector D is given by 3 minus 3 and negative 6 minus negative 2, or 0 and negative 4. And this vector is pointing straight down, which makes sense. If I want to add vectors, I can do this geometrically and algebraically. Let's start with the geometric portion first. If I want to take the vector 5, 3, which is in component form, 5, 3 gives me this vector here. And if I want to add to that the vector 2, negative 1, add this vector to it, what I typically do is say, all right, I find out where vector 5, 3 lands, which is right here, and to that I take and add vector 2, negative 1. In other words, I use the tip of the first vector as my new origin, and to that new origin I'm going to locate the vector 2, negative 1 out in space. So I'm going to go over 2 and down 1. And connect the two. If I were to take then and draw from my origin out to the tip of the second vector I added, that is going to represent the sum and my new vector. This new vector being over 7 and up 2. And if you notice, going over 7 and up 2 would be the same as adding the x components and the y components. So geometrically, you want to add the tail of one vector to the tip of another. Algebraically, add the x components to the y components as long as these vectors are already in component form or rectangular form, if you want to use that verbiage instead. So once again, we have some vector, and this vector could have a magnitude, which we'll typically call r, and some direction, or theta. Its vertical component is given by its y value, and its horizontal component is given by its x value. And we also know that if we need those x and y values, it's just the same as calculating r cosine theta and r sine theta. We've done that before. When we talk scalar multiples of vectors in a component form, for instance, here is the vector a. If I want to look at half a, then it's a vector pointing in the same direction, half as long. If I want to look at 3a, that's a vector pointing in the same direction, but 3 times as long. Likewise, if I want to go the opposite direction, twice as long, that would be the vector of negative 2a. Now look at some of these coordinate values here. If I look at vector A, which is at the point 2, 4, and I look at 3A, you'll notice 3A is located at 6, 12. And 3A just happens to be a multiplication of 3 times 2 and 3 times 4. And that's basically what's going to happen when we talk scalar multiples in component form. You're just going to multiply the x and the y value, or the x component and the y component, by whatever that multiple out in front of the vector is. Next, we're going to talk a little bit about something called unit vectors. And a unit vector is a vector of magnitude 1, which makes sense, just like the unit circle was a circle with a radius of 1. The standard unit vectors are called I and j, I being a vector of unit 1 pointing directly in the horizontal position, j being a vector of unit 1 pointing directly in the vertical direction. And each vector can be represented by the sum of standard unit vectors. So if I want to name the vector 7, 6 by using standard unit vectors, these being my standard unit vectors here, I could say, well, if I take 7 and multiply it by the vector 1, 0, because that's my x component, and 6, and multiply that by the vector 0, 1, or the y component, this is the same as saying 7i plus 6j. And typically I and j will have these vector signs over them. In our book, they'll notate these standard unit vectors with boldface i's and j's and not use the little arrow. Other books will use the arrow for I and j. But 7i plus 6j says the same thing as 7, 6. It's just saying that I and j are these unit vectors. If we want to write AB as a sum of unit vectors, first of all, what I need to do is notice that A and B represent 2 points. So this is a vector out in space. I'll just do a random drawing. Here's vector A, B, like so. And this vector is made up of a initial point of 2, 3 and a terminal point of 7, 20. In other words, we have the coordinates of the tip minus tail, but we haven't named the vector. Let's name the vector first by going tip minus tail. So I have 7 minus 2 and 20 minus 3, and that's going to be my vector AB. This gives me 5 and 17 for that vector AB. And if I want to represent that in terms of unit vectors, I can say that's 5i plus 17j. And that's equal to my vector AB. If I want to find the magnitude of AB, keep in mind magnitude just describes how long it is relative to its distance from the origin in standard position. And if I know it has a horizontal length of 5 and a vertical length of 17, I can find its magnitude. Notice magnitude is given by these double sets of what look like absolute value signs. I can just do a Pythagorean calculation to find out this guy's length. So what I have is 17 squared plus 5 squared, square root that, and that'll give me the magnitude. And that's equivalent to square root of 314. We could simplify that. We could also give it as just square root approximation, and that's going to be 17.7. Now, if I want to calculate a unit vector, notice this doesn't say standard unit vector. This is a unit vector. For any regular vector, there is a calculation that I use of the vector itself divided by the magnitude will give me the unit vector. So here's the vector -2i 4j. So that's roughly this vector right here. And if I want to name a vector that has a length of 1 or a magnitude of 1 pointing in the same direction, I take the vector's coordinates and divide that by the magnitude of the vector itself. So I know that I have a length of 2 on the horizontal, a length of 4 on the vertical. So the magnitude of this vector is given by 2 squared plus 4 squared square rooted, or in this case 2 root 5. And if I want to find the unit vector of this same vector, I take the -2, divide that by the magnitude of 2 root 5, and that's its I component, or its horizontal component. And then the vertical component will be given by 4 divided by 2 root 5. And that's the j. This gives me -1 over root 5i plus 2 over root 5j. Some books will leave it like this, other books will rationalize, giving you root 5 over 5i and 2 root 5 over 5j. Lastly, we're going to write a vector in the form of ai and b times the unit vector j, given that it has a magnitude of 7 and the angle it makes with the positive x-axis is 97 degrees. Well, think about that. Here's my vector, if you will, that is given by a magnitude of 7 and 97 degrees. Well, if I want this in ij form, all I really need to do is find my x and y components. My x components are given by the radius value, or the magnitude in this case, the 7 times the cosine of 97, and my y is given by the magnitude, 7, times the y component of 97 degrees. 7 cosine 97 degrees is roughly 0.85 of the negative type, which makes sense since it's in the second quadrant. And 7 sine 97 is about 6.95. So if I convert those to unit vector form, I have negative 0.85 I plus 6.95 j. A lot of new vocabulary. Make sure we fill out our summary, do your My Math Lab, and we'll talk a little bit more tomorrow.